All right, let's demystify recursion. We're talking about this idea of a function that calls itself. It's one of those concepts in programming that's, both super elegant and kind of mind-bending. Get it right, and you can build some amazing things. Get it wrong, well, things can go south fast.
So let's just ask the big question right up front. What on earth happens when a function calls itself? I mean, really, what's going on inside the machine? It sounds like a riddle, right? But figuring this out is the key to unlocking some seriously powerful problem-solving techniques.
So, to put a label on it, this is what we call recursion. The textbook definition is pretty straightforward. It's a programming technique where a function calls itself to solve a problem. You can almost think of it as an alternative to a regular loop. Instead of saying, do this 10 times, the function just tells itself, hey, do this again.
Okay, let's boil this down to the absolute bare bones. Look at this. You've got a function, we'll just call it f. And what does it do? Inside its own code, it calls f. That's it. That's the whole idea in its simplest, purest form. But you're probably already thinking, wait a second, and you'd be right. There's a big lurking problem here.
And that brings us to the first and biggest problem with recursion, the never-ending loop. What happens when a function just keeps calling itself with no off switch?
All right, let's walk through a super simple example. Imagine a function that does just two things. Step 1, it prints the number 1. Step 2, it calls itself. That's all. So let's hit run and see what happens.
Okay, so the first call kicks off. It does its job, prints 1, and then it gets to step 2. It calls itself, and boom, we're right back at the beginning of the same function.
Now we're in the second call. And what does it do? Well, the exact same thing. It prints 1, and then calls itself again. I think you're starting to see the pattern here, right?
The third call prints 1 and fires up a fourth. The fourth calls a fifth. This thing is just going to keep going and going and going. There's no exit, no stop sign. It's just an endless chain of calls.
And there's a name for this. It's called an infinite recursion. It's a loop that never ends. But here's the thing, a computer can't actually do something forever. Its resources are finite. So, what breaks first?
Well, that leads us straight to memory overload, the call stack catastrophe. Because this isn't just a theoretical problem, it's a very real one that has to do with your computer's memory. Okay, you got to remember this key detail. When a function calls another function, even itself, it has to pause. It can't finish its own job until the one it called is done. So in our infinite loop, we have a growing chain of functions that are all paused, all waiting. Where do they all wait? They get put on something called the call stack. The best analogy is a stack of plates. Every time a function is paused, a new plate is put on top of the pile. It's a little chunk of memory whose job is to keep track of every function that's started but hasn't finished yet. So let's really picture this. Our first function call starts, then it calls itself. But it can't finish yet, right? So, whoosh, it gets put on the call stack to wait.
Then the second function runs, does the same thing, calls a third one. And now it has to wait, so it gets stacked right on top of the first one. Now our pile is too high.
And this just keeps on going. The third call gets stacked on the second, the fourth on the third. Every single time our function calls itself, another plate gets added to the pile. It just grows and grows and grows.
Until, bam, Stack Overflow. You've probably heard that term before, maybe from the website. This is what it means. That stack of plates, that bit of memory, isn't infinite, it's limited. And when our runaway function fills it all up, the whole program just crashes. Game over.
So, how do we actually use this powerful idea without blowing everything up? Simple. We need a stop sign. We need an exit ramp.
And in the world of recursion, that stop sign is called the base case. This is, without a doubt, the most important part of any recursive function. It's just a simple condition, an if statement, that basically says, all right, that's enough, stop calling yourself, we're done here.
Okay, let's look at the difference side by side. On the left, you've got our out-of-control function. On the right, the safe version. And look how small the change is. All we did was add a count to keep track of where we are, and then that critical base case. If our count gets to 3, just stop. Just return. So let's trace this new, controlled version.
We call it, it prints 0. Then it calls itself, it prints 1. Calls itself again, prints 2. Each time it's adding to the stack. But then it gets called with the count of 3. Our base case is met. It stops and returns. And that's the magic moment, because now the function that was waiting for it can finally finish. And once it finishes, the one below it can finish. The stack just unwinds, one plate at a time, perfectly and safely. The program finishes without a crash.
All right, I know all this talk about stacks and calls can get a little heavy. So let's look at a simpler way to visualize all of this. A mental model that'll make your life a lot easier.
Instead of thinking about a pile of plates, a lot of developers think in terms of a recursion tree. It's just a simple diagram that shows the chain of calls, how they branch out, and more importantly, how they come back.
Look at how this tree works. The first call at the top, f of 0, calls f of 1. F of 1 calls f of 2. F of 2 calls f of 3. We go deeper and deeper down the tree until, finally, f of 3 hits our base case. It returns. That allows f of 2 to finish its work and return, which lets f1 finish, and finally, all the way back at the top, our original f of 0 call can complete. See? It's the exact same process of the stack unwinding, just visualized in a way that's much easier to follow.
So, there you have it. We've seen how recursion can be this runaway train headed for a crash, but we've also seen how one tiny little thing, the base case, turns it into a seriously powerful tool. And this isn't just a toy concept. I mean, it's used everywhere. Sorting huge sets of data, crawling through files on your computer, a lot of that relies on this exact idea. So the real question is, now that you get how it works, what are you going to build with it?